Hello class, welcome to chapter 10 of our course. Today we're talking about two sample tests. Okay, so first of all, let's try to get back into it, okay? What did we do in the previous chapters? Well, first you learned how to compute statistics based on a sample of data, right? So this allowed you to describe the central tendencies in your sample. Then you learned how to compute the confidence intervals around those statistics. So it allowed you to add a measure of how precise your statistics really are. And then you learn how to test hypotheses about those statistics. So that allowed you to make and to verify some claims about those statistics. Okay? Now, the next step is comparing two samples. Okay, so now we compare two samples. Until now, what we had was we had a population. We'd take one sample out of that. We would compute a statistic, let's say mean equals 124, and then we learned how to put confidence intervals around those statistics. So let's say the mean is equal to 124 plus or minus 4 with 95% confidence. And then we were able to test some claims. And we could say, okay, given that I know this about my sample, is the mean different from 117? Okay, so importantly, until now, we always just tested our statistics against a fixed number. For instance, 124 tested against 117. Okay, but what happens now in this lecture is that we're going to compare two numbers that also come from a sample. Okay, so instead of just asking whether 124 plus or minus 4 is different from 117, now we're going to say, okay, there's a second sample, the mean of which is 117 plus or minus 8 with a 95% confidence interval, and now the question is going to be, is the mean of the first sample equal to the mean of the second sample? And as you can imagine, that's a slightly different kind of question, and we're going to need to use slightly different math for that. So why do we do this? Well, we do this because comparing two samples is a very frequent situation. Any time that you have an experiment with a treatment group and a control group, those are two samples, and you want to compare these two samples, right? If you're testing a drug, or if you're doing some A/B testing for, let's say, how to best to do marketing in your store, or how to best display things on your internet website, etc. All of that requires having two samples, and so comparing the means or the proportions of two samples. Anything that involves two groups that come from different geographic areas, let's say you want to compare the proportion of elderly people in Georgia and in Florida, then those are two geographic areas, those are two samples you want to compare. A third very common situation is when you have the same group compared over time. So first sample this year, next sample next year, the same people but at different times, those are two samples. Okay, so we're going to have four types of two sample tests. We're going to have population means with independent samples. We're going to have population means with related samples that get compared, or we're going to compare population proportions, or we're going to compare population variances. Okay, so the examples are pretty simple. With independent samples, we're going to be looking at group 1 versus group 2. With related samples, we're going to be looking at the same group, but before and after. With population proportions and population variances, it's just going to be group 1 versus group 2. Let us get started on the first big type of comparisons we're going to make, and that's going to be comparisons of two means of two independent samples. So what we want here is to compare two means, but in order to do that, what we're going to do is to compare their difference. We're going to look at the difference between two means coming from independent samples. So our goal is going to be to test a hypothesis about mu1 minus mu2 instead of testing hypotheses of mu1 versus mu2. And that essentially boils down to asking whether mu1 is equal to mu2. Okay, so we're going to have test hypotheses about mu1 minus mu2, or we're going to form confidence intervals for the difference between mu1 minus mu2. So the point estimate for mu1 minus mu2, well, unsurprisingly, it's going to be x1 bar minus x2 bar. The same, it's going to be the difference in the averages that we compute from our samples. So that is simply the difference of the averages. And once we have our point estimate, we're going to do the same thing we always do. We're going to do either two-tailed tests of our point estimate, or lower tail test, or upper tail tests of our point estimate. Our point estimate is mu1 minus mu2, and we test whether mu1 minus mu2 is equal to 0 or different from 0. Or we test whether it is greater than or equal to 0, or less than or equal to 0. But of course, what we are actually looking at is mu1 versus mu2, right, in these situations. And everything is going to work the same way as it did before for just a single mu. Now we're looking at the difference between two mu's, but we're going to do it in the same way. So in a two-tailed test, we're going to compute a test statistic, and we're going to check whether it falls inside of a rejection region, here and here, or whether it falls in the middle in a non-rejection region, right, as we compare it to some critical values. Same for a lower tail test, same for an upper tail test. Now we're actually going to have two subcases to look at. Subcases. In both subcases, we are going to assume that mu1 and mu2 are unknown in both cases. However, in the first case, we will assume they are equal, and in the second case, we will assume they are not equal. Okay, when they are assumed equal, we're going to use what we call a pooled variance t-test, and when they are not equal, we're going to use what we call a separate variance t-test. And in this lecture, I'm going to explain the pooled variance t-test in detail. So let us look at the pooled variance t-test in detail. So again, this is a test for the difference between mu1 and mu2, assuming that we do not know sigma 1 and sigma 2, but we assume that they are equal. So the assumptions are that the samples are randomly drawn and independently drawn, that the populations are normally distributed, or that we have sample sizes that are at least 30. So that's the same as we had before, but now we have it for both samples. And the third assumption is that the population variances are unknown, but they are assumed to be equal. So just as we had before, we need to compute a test statistic, and that test statistic is based on a variance. Now in this case, the pooled variance is expressed with this. We call it S squared P. P stands for pooled. And what is the pooled variance? Well, it's a combination of the variance of our first sample, S1 squared, and the variance of our second sample, S2 squared. Really, if you look at this formula, it is just a sort of weighted average of our two variances. So we're going to compute this test statistic, and it's going to be used exactly in the same way as we used test statistics before. Okay, so we have a new type of S, which is just a combination of S1 and S2, but it functions the same way as the S we had before. And our test statistic is essentially the same thing we had before, right? X bar minus mu divided by S over square root of n, but in this case, we are computing something that is similar, but based on mu1 minus mu2, the difference between the means. And the last thing we need to know about our t-stat is the degrees of freedom. And in this case, the degrees of freedom are n1 plus n2 minus 2. In other words, it's n1 minus 1 plus n2 minus 1, right? So it's similar to what we would have had with one sample, it's just now we're adding them up for the two samples. Okay, so what do we do with that t-stat? Well, we do the same thing as before, right? We'll compare it to a critical value. That critical value will be coming from a t-distribution with degrees of freedom n1 plus n2 minus 2. What does that look like? Well, it looks the same as before. In a two-tailed test, we're going to reject when we're out on the tails, out here and out here, where each of the tails has half of alpha in probability. In a lower tail test, we're going to be looking at just this lower tail. In an upper tail test, we're just going to be looking at this upper tail. Everything else is very similar to what we know from before. Now let us do an example. So imagine you're a financial analyst and you work for a brokerage firm. You're trying to see whether there is a difference in dividend yield between stocks that are listed on the NYSE and the stocks listed on the NASDAQ. Well, let's say you've collected the following data. So you have 21 stocks from NYSE, you have 25 stocks from the NASDAQ. You have a sample mean and a sample standard deviation for each of your samples. Right? So now, assuming that the populations are approximately normal and that their variances are equal, so this is our first case scenario, can we find that there is a difference in the mean dividend yield? So first things first, what is our hypothesis? Well, our H0 is going to be mu1 minus mu2 equals 0, right? Meaning we're trying to test whether mu1 is equal to mu2 versus H1, which is that they are different. So we have a test statistic, which is computed with this formula that I just showed you. Just to put a fine point on it, where does this SP, this is our pooled variance, where does this SP squared come from? It comes from this formula. Okay, this formula, this is not complicated, we just plugged in these values, right? Those values that we just plugged into the as a pooled variance formula. So we have our t statistic, our test statistic. What do we compare that to? We compare that to a critical value in a two-tailed test. Which critical value do we use? Well, we use a t that has alpha 0.05 and degrees of freedom equal to n1 plus n2 minus 2 equals 44. Okay, so we can compute that. Those are critical values either out of the tables or using Excel like you've learned in the previous chapters. And so what do? All we have to do is compare the values, right? So 2.040, where does it fall on that spectrum? Does it fall higher or lower than the critical values? Does it fall in the rejection region or not? Well, it falls squarely into the rejection region because it is higher than our critical value of plus 0.0154. Okay, so it falls out here and we can make our decision. We reject H0, so we can conclude that there is evidence of a difference in means. So now some of you might ask, what about the p-value approach, which was the second way that we could make a hypothesis test? Well, it also works. Now that you have your t-stat, all you need to do is find the p-value, which, if you remember, is just the probability of having found a t-stat that is like the one you found or more extreme. So in this case, it's going to be the probability of a t-stat being less than minus 2.040 or greater than plus 2.040 if we have a t-distribution with degrees of freedom equal 44. So we have the probability of t being below the t-stat we found, it's equal to 0.0237, or the probability of t being above plus 2.040, the positive side on our t-stat. And the p-value is the sum of those two probabilities, and it's 0.0474. And as you remember, the p-value being below 0.05 means that out of 5, with 95% confidence, we can reject because the p-value is lower than alpha. So how is this going to look in Excel? Well, you're going to have a spreadsheet that already does all these calculations for you. Now, these calculations, what are they? They're the same calculations that we just went over together. So you first calculate your pooled variance, then you plug that into your standard error, then you add the numerator x1 bar minus x2 bar minus the difference in the mu's, and that is your test statistic. And once you have your test statistic, you can compute your test here, either comparing to the critical value or computing the p-value and checking whether it is higher or lower than alpha. Either way, your result gets displayed right here. So what about that third way, the confidence interval approach? Well, of course, yes, it also works. Now, the confidence interval for mu1 minus mu2 is very similar to what we've previously done. So this works the same way as before, except that now we are looking at a difference between mu1 and mu2 rather than just a single mu. But that is the same formula. You should be able to recognize that. This formula right here is essentially the same thing as x bar plus or minus t half of alpha time s over square root of n. You should see the resemblance. Okay, so plugging in the numbers, we get our confidence interval right here. 0 is less than the entire interval, and we are 95% confident that the mu of the NYSE is higher than the mu of the NASDAQ. What does this look like in Excel? Well, again, you're going to have these templates, and you will use them the same way as you did for one sample. Okay, so earlier I said that we had two sub-cases. The second case is when we do not assume that sigma 1 and sigma 2 are equal. So we still have samples that are independently drawn. We still have populations that are either normally distributed or sample size greater than 30. However, this time we assume that the variances are not equal. So what do we do in that situation? Well, this test is known as a separate variance test, as opposed to what we had before, which was the pooled variance test. But the formulas for this test are a little bit more complicated, and so we're not actually going to go over them. All you're going to have is the spreadsheets on Excel. So you will get a template just like this one. The difference with the previous template is that here it will say separate variance t-test, the same way as the first one will be saying pooled variance t-test. And you will have to know when to choose separate variance and when to choose pooled variance tests. So notice here that you could do the exact same test as we just did before, but with the assumptions that the variances are different. In particular, here you have the same data from the NYSE, the same data with the NASDAQ, but you do not make the assumption that the variances of the two are equal. And in fact, as you see, the numbers are slightly different. So in this case, we filled in the test in the same way, however, it's a separate variance test, and so the calculations are a little bit different. And what do you see? Well, when we tested this as a separate variances test, we do not reject the null hypothesis. So this tells us that the separate variance test is a little bit harder to pass than the pooled variance test because it makes fewer assumptions. Okay, so now that we've looked at how to compare two independent samples, now we're going to look at how to compare two related samples. So these will be tests for two related means instead of independent means. So when we say we have related population, what we mean is that the observations in the two samples can be paired. For example, let's say you collected data twice on the same individuals or items. Then the first time you collect variable x for subject I, we will call that x1i. And the second time you collect that same information for the same person, we will call that x2i. And those can be people or they can be items. Now, if they were independent, we would just compare x1 and x2 just the way we did in the first part. However, now we're going to consider the fact that these two are observations of the same variable for the same person. And the way we're going to do this is we're actually going to compute the difference between the paired values. So we're going to compute a new variable d, and each observation of d is going to be a di, which is going to be equal to x1i minus x2i. In other words, it's going to be the difference between the paired values. D is going to be the before-after difference of our two samples. Now this is a very powerful approach because it eliminates the variation among the different individuals or items. Now we are just looking at the change in the variable of interest, which is x. The assumptions are going to be the same as we always have, which is that either differences are normal or we have a large sample. So we calculated d for each of our observations, and we can treat it exactly the same way as any single variable. So we're going to calculate the mean of d, which we will call d bar. So d bar is just the average of our differences. And we can treat it the same way as any other variable, and we can compute a standard deviation for d. We will call that SD, and is computed in the same way as we usually do it for any x variable. So by now you're starting to get it. We can also compute a t-statistic for d, and this should look very familiar, because it is exactly the same formula as we did in previous chapter with a single variable. And in the exact same way as we did for a single variable x, we can do a two-tailed test, or a lower tail test, or an upper tail test on our new variable that we call d. And in the same way that we computed a confidence interval for a single variable x, we can now take a confidence interval around the mean of our new variable called d. So again, this should look very familiar. So let us have an example. Assume you have 5 salespeople and you have sent them to a customer service training workshop. Your question is whether that training workshop has made a difference in the number of complaints against your salespeople. So your variable of interest is the number of complaints, but you recorded the number of complaints before and also after. So you have 2 observations of the number of complaints for each individual in your sample. Therefore, these are paired samples. For each salesperson, you can compute the difference between before and after. That difference for each person I is called di, and the variable is called d. So if you look at the values for d, you see that they are all negative. It looks like the training worked. However, these results might just be a fluke. You would need statistics to know whether this training really made a difference. In other words, you want to test whether that difference d is statistically significantly different from 0. So what do? Well, you treat d the same way as you would have treated an x variable previously. So you compute an average, d bar. It is just the average of the differences. Then you compute a standard deviation, SD, which is computed the same way as you did before. It is the square root of the sum of squared deviations from mean divided by n-1. And then you can run your test. So let us set it up first. What are the hypotheses? Well, you are trying to see whether the before-after difference is equal to 0 or not. So your hypothesis, H0, is mu d equals 0, and your H1 is mu d different from 0. What are your critical values? Well, this is going to be a t-test. It's a t-test at the 0.01 level, so alpha equals 0.01. The degrees of freedom are 1 less than your number of observations. We have 5 observations, so the degrees of freedom are equal to 4. And so your critical t is a t half of alpha equal to plus or minus 4.604 right here. What is your test statistic? Well, same as before. We used to do this with x. Now we do this with d. We just plug in the numbers, and our test statistic is minus 1.66. And so now we're going to compare where that t-statistic falls in relation to the critical values. We can picture this graph in our heads. We see that minus 1.66 is in between the 2 critical values, and so we fail to reject the hypothesis. Of course, the p-value approach would also work here. So you would sum the 2 probabilities on each side, and you would find a p-value of 0.173, which is not less than alpha, which was 0.01, and so you cannot reject. And naturally, the confidence interval approach would also work, and you find that 0 is included in your confidence interval, and so again you fail to reject. What would this look like in Excel? You would have a template and it would look something like this. In this case, you would have used the two-tailed test, but of course you also have a lower-tailed test or an upper-tailed test. Last note on the paired test. Sometimes the exact same data can be thought of as unrelated or as paired. So what is the difference? Well, in the second case, you actually have the information that you would need in order to pair. In the first case, you don't know whether these observations are in fact related to the same person or not. So if you do have that information, should you use a paired test or not? Well, the answer is yes. The paired test is a lot more powerful. And as a rule of thumb, if you have more information that you are able to use to do a test, you should use that information. A little hint for your homeworks and tests. Pairing requires N1 equal N2. Your before and after samples have to have the same number of observations. So if you see N1 different from N2 in your two samples, you cannot pair. Don't waste your time wondering whether this could be a paired test. So we've arrived to part 3 of the chapter where we compare two population proportions instead of two population means. Now the goal here is going to be to test two proportions coming from two samples. We assume that these samples are independent. Pi1 is the proportion from the first sample, pi2 is the proportion of the second sample. And instead of comparing them one against the other, we're going to compare their difference against the 0. There are some assumptions underlying these kinds of statistics, and we have a rule of thumb to check whether these assumptions hold or not, and that is n1 pi1 greater than 5, n1 1 minus pi1 greater than 5, and the same for n2 pi2 and n2 1 minus pi2. This should look quite familiar. It is the same check that we used to do with just one sample and one proportion. The point estimate for our difference is going to be p1 minus p2, where the p's are simply the proportions that we calculate inside of our samples. So p1 minus p2 is the estimate for pi1 minus pi2. The null hypothesis is going to be that the proportions are the same, meaning pi1 equals pi2, or in other words, pi1 minus pi2 equals 0. Then we're going to compute something we call the pooled estimate of the overall proportion, and that is x1 plus x2 divided by n1 plus n2. Remember that when we are talking about proportions, x is the number of items of interest. So x1 is the number of items of interest in the first sample, x2 is the number of items of interest in the second sample. This p-bar is just like a new measure for the proportion, a new measure for p, that is the proportion taking both samples together. The number of items of interest on the whole divided by both sample sizes. Remember that tests for proportions are z-statistic tests, so we are using the standard normal, and so we're going to compute a z-statistic. It should look fairly familiar because it is of the same form as we always compute. It is something that we computed, p1 minus p2, minus the hypothesized values, pi1 minus pi2, in this case it's going to be 0, and it's divided by some big square rooted term. In this case, the square rooted term is this one. You don't need to remember it by heart, but you should recognize the form it has. And of course, we're going to be able to do two-tailed tests, or lower-tailed tests, or upper-tailed tests. And we're going to make our decisions, and we are going to use the same criteria to either reject or fail to reject our H0. So let us do an example. Imagine you want to know whether there is a significant difference between the proportion of men and the proportion of women who will vote yes on a given proposition. You took a random sample and you found that 36 out of 72 men and 35 out of 50 women indicated that they would vote yes on that proposition. So the hypothesis for the test is that the proportions are equal. That's our H0. Pi1 minus pi2 is equal to 0. And the H1 is, of course, pi1 minus pi2 different from 0. The sample proportions are 36 out of 72 for men and 35 out of 50 for the women. And the pooled estimate, the p-bar, is simply the proportion, taking both samples together, x1 plus x2 divided by n1 plus n2. We can compute the z-statistic by plugging in the values into the formula I showed you earlier, and we obtain minus 2.20. We have critical values. This time, remember, this is based on a standard normal, so you recognize the critical values. At 95% confidence, this is plus and minus 1.96. And we know our decision well because minus 2.20 is inside of the rejection zone, then we are able to reject the null. In Excel, it's going to look like this. We're going to have a template. Note that, of course, the p-value approach also works here. And the confidence interval approach also works. This is the formula for your confidence interval around p1 minus p2. Again, it's simply a slight variation of something you've already seen before. And these are the results of plugging in our values into the confidence interval, and as you see, 0 is not included in the confidence interval. Okay, so this brings us to the last part of this chapter, which is comparing two population variances. So the first thing is, why is this important for us? Well, because it loops back to the very first part of this lecture. Remember, in part 1 we said we have pooled variance and separate variance tests. Pooled variance test when we think the variances might be the same, and separate variance tests when we think the variances are different between our two samples. So if you want to be able to choose between those two, you need to be able to test for whether the variances are the same or not the same. And so we are going to test the variances, and if we find the same variance, we'll do a pooled variance test. If we find differences between the variances, we'll do a separate variance test. So in order to test whether two variances are equal, we are actually going to test their ratio. So if our hypothesis H0 is that sigma 1 squared equals sigma 2 squared, we are actually going to use the ratio S1 squared over S2 squared as a test statistic. Okay, the same way, if we are just doing a one-tailed test, we're going to look at sigma 1 squared less than or equal to sigma 2 squared. We're also going to use this F statistic S1 squared over S2 squared, where S1 are respectively the variance of sample 1 and the variance of sample 2. Now, importantly, S1 and S2, or sample 1 and sample 2, in this case, are not just in random order or in whatever order you got them from your data. Sample 1 has to be the sample that has the larger variance, and sample 2 has to be the one that has the smaller variance. So if they happen to come to you in the opposite order, you just flip them around just to make sure that the higher S is on the numerator and the smaller s is in the denominator. So this ratio, S1 squared over S2 squared, is called the F-test statistic. And now, this is a new distribution that we haven't talked about before. So far we've talked about z distributions, we've talked about t distributions, and now we have a new one called the F distribution. So even though it is a new distribution, it is going to function roughly the same way as the other two. So the F critical values will be found from an F table, the same way we had z critical values from a z table and t critical values from t tables. To read a value out of an F table, you need 2 degrees of freedom. There's the degree of freedom of the numerator and the degree of freedom of the denominator. Now again, the sample variance that is bigger has always to be the numerator, not the denominator. So for your F stat being S1 squared divided by S2 squared, the first degree of freedom is N1 minus 1, the sample size of the first sample, and the second degree of freedom is N2 minus 1. So in your F table, the numerator degrees of freedom are the columns, and the denominator degrees of freedom are the rows. I'll show you that right here. As you see here, you have degree of freedom 1, so this is numerator degree of freedom, and this is df2, the denominator degree of freedom. So a couple of notes here. First, note that the F table has to skip some numbers, otherwise the table would get huge. So here at the bottom, you see it goes from 28 to 29 to 30, but then it goes from 30 to 40, and from 40 to 60, etc. The second thing is that you shouldn't be surprised if you see very large values, particularly here up the top. When the degrees of freedom are very low, the F distribution tends to give you really large numbers. So what does the F distribution look like? Well, this is the shape of the F distribution. And so we have two types of tests, which are the equality test, sigma 1 squared equals sigma 2 squared. And in that case, we reject if our F stat is higher than this critical value. We reject in this zone up here, okay? And we fail to reject down here. Now for an inequality test, where we test sigma 1 squared less than sigma 2 squared, we are also going to reject in this same area up top here, except in this case, we're going to reject above f of alpha rather than f half of alpha, okay? But you notice one thing. Both of those are only on one tail. There are no two-tailed tests here. Why? Because the f is not symmetric. And that is the reason why we always want to have the numerator being bigger than the denominator, because in that way we ensure that we are only looking at numbers that are greater than 1, and we are always looking on the same side of the distribution. So we will never do a low tail test. So let us do an example here. Imagine you are a financial analyst for a brokerage firm. You want to compare the dividend yields between the stocks on the NYSE and a NASDAQ. Same thing as before, we already saw this data. Now, remember, we weren't sure whether we should consider the standard deviations to be equal or to be unequal. Remember, we did both tests. We did a pooled variance test and we did a separate variance test. So now what we're going to do is we're going to test the variances, and that will let us know which test was actually appropriate. And so we're going to run our test. First, we decide what our hypotheses are, and it's H0, the variances are the same, versus H1, the variances are different. Then we find the critical value. Here we want an alpha equal to 5%. We look at the numerator degrees of freedom and the denominator degrees of freedom. They're respectively 21 minus 1 and 25 minus 1. And so we find our critical F, which is an F statistic for half of alpha, which is 0.025, 20 degrees of freedom and 24 degrees of freedom, and that is equal to 2.33. That could have come out of the table, or it can come out of Excel. And now we compute our test statistic. Our test statistic is very easy to compute. It's S1 squared divided by S2 squared. Remember from the table, S1 was 1.30, S2 was 1.16. Remember, we want the bigger variance at the top. So 1.30 squared divided by 1.16 squared is equal to 1.256. Where does 1.256 fall? It is lower than our critical F, and therefore we fail to reject the hypothesis. And so our two sigmas can be considered to be equal. In other words, there is not enough evidence to prove that they are different. What would this look like in Excel? Again, there would be a template, and you would fill in the information relating to the larger variance sample here and the smaller variance sample here. So to conclude this chapter, what did we see today? First, we learned about comparing the means of two independent populations, and we saw that there was two ways to do it, either a pooled variance t-test or a separate variance t-test if the sigmas are considered to be different. Then we looked at what to do when the populations are related and we want to compare their means, and this is what we call a paired difference test, and it was also a t-test. And then we looked at how to compare the proportions of two independent populations, which was with a z-test, and then we compared the variances of two independent populations, which was done with an f-test. And finally, we looped back and showed that using this f-test is how we are going to decide whether to use a pooled variance or a separate variance test when we test the means of two independent populations. And that concludes Chapter 10 about hypothesis tests with two different samples.